And now we'll go on to page 2, the backside. So looks like this with no further ado. So a fair coin is to be flipped 5 times. What is the probability that the result will not be heads, or 5 heads in a row? I just want to ponder that again. We don't want 5 heads in a row. Well, that should be a pretty high probability. It should be pretty close to 1, because I think if I were to take a coin and just flip it 5 times, the chance that I see 5 in a row is unlikely. So let me rephrase that. The chances that I won't see 5 in a row is pretty darn likely. I would say that's very likely to happen. So I'm kind of estimating my answer here is that I should get a pretty close value to the number 1 in the final answer here. But I'm going to start now by giving a bogus solution that a lot of students tend to say. If the answer is not 5 heads, they end up calculating the probability of all tails, meaning, well, you don't want 5 heads, so you want tails, which is a half and a half and a half and a half and a half multiplied together, which is 1 out of 32. But I'm arguing that that answer doesn't seem reasonable because we already estimated that our number should be close to 1, and 1 out of 32 is a number that's close to 0. So this answer does not even seem reasonable. Again, in real life, flipping a coin 5 times, yeah, there is a chance maybe someone will do it and get 5 heads. But I think for most of us, if we repeated the experiment over and over and over again, we would not see 5 heads in a row. So more than likely, we're not going to see 5 in a head in a row. This probability should be high, not low, like 1 out of 32. So let's find the error here. All right. So the incorrect answer is 1 out of 32. Not getting 5 in the row, not getting 5 heads does not mean they all have to be tails, but it does mean that we want at least 1 tails, or 1 must not be heads. But that's kind of weird to say 1 must not be heads. I think most of us would just say 1 must be tails. All right, at least 1 must be tails. Maybe you get 2 tails, maybe you get 3 tails, but not all heads means at least 1 must be not heads, which is tails. And so now what I'm going to do is kind of look at the sample space and say, all right, here's the example of getting 5 heads. I could also list some outcomes that get 4 heads. So there might be heads, 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 then tails, or heads, heads, tails, heads, heads. There are many outcomes that have 4 heads. I just listed a few, and the ... means there are others. We can continue on after we list all the outcomes that contain 4 heads and start listing the ones that contain 3 heads. For instance, heads, heads, tails, tails, and so on and so on. There are more. We could then go on and calculate the probabilities or the outcomes that have 2 heads, all the outcomes that have just 1 heads, and then all the outcome that have 0 heads, meaning we would have all tails. All right, but we're technically right now looking at all the outcomes that are possible when you flip 5 coins. I mean, not visually seeing every single one of them, but at least structuring 5 heads or 4 heads or 3 heads or 2 heads or 1 head. That's what's going to happen, something in that sample space. Now, we're concerned with not getting 5 heads in a row. So here's our entire sample space. That something in there is going to be going to happen. So that's 100%, but we don't want 5 heads, which means we want anything in that. All right. We want to count all the outcomes that I've circled in mustard, orange, yellow there. So that is a lot of calculations. The last unit we talked about considering complements. Right? So I'm going to make a connection to kind of what we did last unit when we considered complements. All right, so from here I'm going to rewrite everything I've explored so far as follows. When we flip a coin 5 heads, you may get no heads, or you can get 1 head, or you might get 2, or you might have 3 or 4, up to 5. But if we add all those probabilities, they must equal 1. And I can say that the probability of 1 heads plus 2 heads plus up to the probability of 5 heads, all of those can be classified as the probability of getting at least 1 heads. So the probability of no heads plus the probability of at least 1 heads must equal 1. And with some basic algebra here, we can show that the probability of at least 1 heads, we subtract no probability of no heads from both sides, and we end up with this equation. And at this point, I've done a lot of the legwork. I've done my point to give some background about what it means to find the probability of at least one of something, which is really my ultimate goal. If you're kind of reading down on the worksheet, we're going to define that in a minute. So I'm going to leave this as an open question. If you're concerned or you're curious, maybe might be a better word, about what the actual answer here is, I want you yourself to try to calculate it. All right. The answer is, I'm not going to give the solution, but I will tell you that the answer is 31 out of 32. And again, going back to our estimation at the beginning, it should come out to be a value pretty close to 1, and 31 out of 32 is a value that's pretty close to 1. So I just wanted to leave you with that question to ponder on your own. And if you really are stuck and you want me to work through it with you, send me an email and I'll gladly do that. But the main point of that was to give an example, some background exploration in finding the probability of at least one of something. And so we'll move on to the worksheet now, and you can find this in your book. But as described before, the probability of an event happening at least once is 1 minus the probability that the event does not happen. And so now let's look at another example. The probability that a region prone to flooding in a single year is 1 out of 10. What is the probability of a flood 2 years in a row? So the key word here is that in any single year, the probability of flooding is 1/10. That is key clue that this is an independent event. And from earlier in this unit, in this section, I should say, the probability of independent events, the probability of a flood in year 1 and in year 2 is found by multiplying. So 1/10 times 1/10 becomes 1/100th. What is the probability of no flooding for 10 consecutive years? Oops, let me back up there. And 1/100th is 0.01 is a decimal or 1%. So I just put that out there because I know some of the homework questions, or I'm pretty sure some of the homework questions asked you to express as a decimal or as a percentage. So you can always use your fraction to convert to a decimal and then into a percent. Now, what is the probability of no flooding for 10 consecutive years? So we want no flooding in year 1, no flooding in year 2, and no flooding in year 3, all the way up to no flooding in year 10. So that becomes, well, if the probability is 1/10 of flooding, we consider its complement of you're either going to flood or not flood. So if 1/10 is the probability of flooding, then 9/10 is the probability of not flooding. So we have 9/10 times 9/10 times 9/10 times 9/10, 10 factors of 9/10, which we can write as 9/10 to the 10th power. and definitely going to use a calculator to estimate the decimal here. So 9/10 to the 10th power is approximately 0.35 or 35%. Okay. Lastly, what is the probability of flooding at least once in the next 10 years? Oops, going back here. So 9 out of 10 to the 10th power is the exact answer, but you are probably going to be asked to estimate it to the nearest percentage or 2 decimal places. Let me just back this up for a moment. So now the probability of flooding at least once in the next 10 years. So now we can apply what we just looked at. The probability of at least once is calculated as 1 minus the probability of none, of the event not happening. So the probability of no flood. And in a moment, in the question above there, we've calculated the probability of no flooding as about 35%. But here's the exact answer: 1 minus 9/10 to the 10th roughly estimates to 65%, 0.65. But that's it. The main point of that example was to show that to calculate the probability of something occurring at least once is almost always calculated by computing the probability of 1 minus the probability of none. Very wordy, but 1 minus the probability that it won't happen. So in closing here, I have a table from the textbook that shows the marital status of the U.S. population ages 15 or older in 2015 in millions. We've seen tables like this a few times, and we're going to calculate some probabilities that are asked of us, and they include topics from both this section and the last section. So with no further ado, and one other thing I wanted to mention here is that I am not going to simplify any of my answers in this. I kept them as a fraction. If I needed to simplify, I could. If I needed to put them as a decimal, I could. If I needed to put them as a percentage, I could. I just, for time's sake, did not simplify my answers. But if I was asked to, I could do it. So just keep that in mind as we go through these. So if one person is selected from the population, find the probability that the person is not divorced. Well, the first thing I wanted to highlight is that we've seen this before. This bottom number in the corner, 254, represents how many people in total were surveyed. So if we're concerned with the ones that are not divorced, we're going to find the column titled, well, I don't see anything not divorced. I find a number that is divorced, 26. So if there are 254 total respondents, but 26 are divorced, that means 254 minus 26 out of 254 is the probability of selecting one not divorced, which comes out to be 228 out of 254. We need to find a probability of two events separated by the word or. We want to think addition, but we also want to consider, are these events mutually exclusive? And being widowed or divorced, you can't be both, right? So these are mutually exclusive events. Therefore, we just calculate their probabilities by adding. 14 out of 254 were widowed, 26 out of 254 were divorced. Adding those together, we find that the probability of selecting someone either widowed or divorced is 40 out of 254. Just another example of really the same thing. They have never been married or are divorced. Again, those are mutually exclusive events. 81 out of 254 have never been married. 26 out of 254 have been divorced. Adding those together, we get a total of 107 out of 254 as the probability of selecting someone that has never been married or divorced. Now we're going to look at an example where we do have, or we have two events that are not mutually exclusive. So selecting a female or being divorced. We could definitely select a female that is divorced. So from last section, the probability of selecting a female is 131 out of 254. The probability of selecting someone that's divorced is 26 out of 254, but we must subtract the intersection, 15 out of 254. There are 15 women who are counted in both those previous probabilities, so we need to subtract out the overcounting for a final total of 142 out of 254. And just some practice with conditional probability. Suppose we want to select a female given that the person is. So here is an example of applying conditional probability. The condition is we selected someone who's divorced. Given that we have someone who's divorced, what's the probability that they're female? Well, given that they're divorced, that means we have 26 people. That's the given information. That's what has happened. That becomes our denominator. Now, of that, of the divorced people, how many are female? We look above and see that those 26 people are comprised of 15 female, 11 male, but we're concerned with selecting a female. So our probability of a female, given that we have selected divorced, is 15 out of 26. What's the probability of selecting someone who's divorced, given that they're male? Again, we have a total of 123 men, and we're told that's what we're given. We've been given a man. So that becomes our denominator. And now of those 123, 66 are married, 43 are never married, 11 are divorced, and 3 are widowed. We want to calculate the probability of divorced. So our final answer is 11 out of 123. And lastly, we're putting two kind of theorems, two probability rules together. What is the probability that they have never been married or married, given that this person is a woman? So again, our given information becomes our denominator, 131. And never married or married are mutually exclusive events separated by or. We're going to add the two values together. So never married out of the 131 is 38 respondents, and married out of the 131 is 67. So 38 plus 67 becomes our numerator for a total of 105 out of 131, the final probability. So you'll see at this point, we have completed. I can't switch out on my screen here. Why not? Sorry for this delay. Oh, well, there we go. So at this point, we're done with the main lesson. Okay. That's what you're responsible for. That would that's the content that you'll see on the final exam, our last exam. That's what is absolutely required for you in this course. That's what you'll be expected to do in the homework. What I'm hinting at is I posed 2 challenge questions, and you can totally just not do them at all. All right. But bored and maybe looking to challenge our minds, or that last time I gave a challenge question, I had students sending me emails and little texts that they enjoyed the problem solving or the puzzle part of it, particularly the question about the 3 boxes of fruit. that were mislabeled, if that rings a bell from earlier this semester. So what I'm hinting at is today's lesson or this lesson is done, but those 2 challenge questions are completely optional for you to ponder on yourself, play along, challenge your mind. I will tell you that they are challenging. All right. Again, they're not required for this course. And if you'd like to shoot me an email with your answers or discuss, I'm happy to keep myself occupied and have a discussion with you, but I'm not going to provide a solution or an answer to them. That would defeat the purpose of posing a challenge. It's for you to, read them, maybe play around with it. There's no expectation that you have to do them. And I can tell you one of those questions, I had to read, put it away, read, come back to it, had to do some thinking. It wasn't anything obvious for me, but I don't want to make this video any longer than it needs to be. So please take care of yourselves, and I'll see you for our next lesson.